Good morning. Today we are going to learn about some resonance phenomena in nuclear reactions that is well described by Breit Wigner relations. And in this lecture we are going to learn about Breit Wigner one level formulae. I am Dr. Raghu A, working at Government College Autonomous Mandya. This is the outline of the today's lecture. Basically we will be discussing about the Breit Wigner relations, and later we generalize the Breit Wigner formulae. Let us revise the necessary things for the lecture. Logarithmic derivative, which is a dimensionless quantity denoted here as rho L, for the nth partial wave at the surface of interaction is defined as the ratio of derivative of wave function UL with respect to R exact at the surface R equals R, and that divided by 1 by UL. So that is the definition of logarithmic derivative, which is basically a dimensionless quantity. So that is for the nth partial wave. For S wave, L equals 0, one can easily get the rho naught. And this rho naught can be used to describe inelasticity parameter, which we have studied earlier, and it can be easily expressed in terms of inelasticity parameter. So using that, one can get the scattering cross section in terms of logarithmic derivative, which will be like this. Scattering cross section is equal to pi by k square into modulus of e power 2 ikr minus 1 plus 2 ikr divided by rho naught minus ikr modulus whole square. This is basically the expression pi by k square into modulus of 1 minus eta naught whole square. So that expression is rewritten here, in which eta naught is replaced by logarithmic derivative for S wave. Similarly, this reaction cross section can also be expressed in terms of logarithmic derivative, and that expression will be like this: pi by k square times minus 4kr into imaginary of rho naught divided by r of rho naught square plus I of rho naught minus kr whole square. This I here is actually refers to imaginary part of rho naught, and r here refers to real part of rho naught. Basically, rho naught logarithmic derivative is a complex quantity. So those two relations are important. We will be using that. And let us study basics of compound nuclear reactions. So compound nuclear reaction is one in which it involves two steps: formation of compound nucleus and its subsequent decay into products. So formation of compound nucleus is by the projectile incidenting on the target. A is projectile, capital A is target. That forms a complex nucleus. Many times complex nukes will be in the excited state, therefore it is denoted as C star here. And this compound nucleus, which is unstable, will decay into its products. Lowercase b is the ejectile and uppercase b is the recoil nucleus. So combiningly, the two particles A plus A used to form compound nucleus is called as formation process, and the reactants B plus B are actually called as the reactant products, reaction channels. Okay, they are also called as the entrance channel and exit channels via the formation of the compound nucleus. So entrance channel, now we can call it as some letters alpha, and exit channel is normally denoted as beta. So alpha itself is actually a combination of reactants A, and beta is again maybe 2 particles or 3 particles. It's the exit channel from the compound nucleus. Now Heisenberg uncertainty principle can be used to relate many parameters. Basically, the width Heisenberg uncertainty principle, it can be expressed in many different forms. One of the forms is the product of the energy times time, which is really equal to h cross. So at the minimum uncertainty, they are equal. That's written here in this form. Gamma tau equals h cross. This is the Heisenberg's uncertainty principle. Gamma has the dimension of energy and tau has the dimension of time. At the minimum uncertainty, their product is h cross. Or it can be written in this manner. Gamma equals h cross by h cross times lambda. The lambda is 1 by tau. Tau is the lifetime of the state which is created due to the formation of compound nucleus. Higher the lifetime, then lambda will be lower. Lambda is called as decay probability. So lambda equals 1 by tau. In fact, gamma is called as full width of maximum, which is measure of energy. That's given by h cross lambda. So this same compound nuclear reaction can also be written in terms of energetical diagram. So energy is plotted here from bottom to top. A plus A is at some certain energy. When those two interact, they form a compound nucleus which will be normally at higher energy, and that compound nucleus, because it's unstable, it will undergo a decay process with the emission of two particles B plus B, and the C star is excited state and its ground state is given by C, which will be a reference line for the 0 MeV for the compound nucleus. And this compound nucleus either can decay along the B plus B channel or it can decay some other channel. So the Q value is normally measured from the mass energy. This difference between the mass energy of the reactants and the product defines the Q value. That Q value in this diagram is actually positive, and therefore it is exothermic reaction. That Q can be negative also depending on the relative positions of product and the reactants. So compound nucleus can either go decay to one of those state B plus B, or it can just de-excite to ground state with the emission of gamma. That's another decay channel. Or the compound nucleus can also decay back to the same reactants A plus B. So in principle, a compound nucleus can undergo decay in any of the possible channels. So if each of these decay channels has a partial width of gamma I, then the total width can be written as algebraic sum of all the partial width. So that's an important expression for total width. Now let us study the important case of Breit Wigner relations. So while deriving that, we make this case very simple. So first assumption is only neutron induced reactions are considered here. So only neutron induced reactions means only nuclear interaction will be present here, because neutron is a neutral particle and therefore Coulomb interactions will be absent. Only low energy interactions will be studied initially here. So low energy means only lowest possible partial wave will be included in the interaction, and that is L equals 0, S wave interactions will be considered here. Third one is spins of projectile and target are ignored. For the time being, let us ignore the spins of projectile and target. Let us assume that their total spins may be 0. Okay, so with those three assumptions, now we can start deriving expression for Breit Wigner relations. Let alpha and beta be the only two decay channels with partial widths gamma alpha and gamma beta. Okay, then the formation of compound nucleus and its decay can be written like this. So compound nucleus can be formed through alpha channel. After forming this compound nucleus either can decay to beta or it can decay to alpha. Now for the simplicity, we are assuming only two decay channels for compound nucleus. So if that is the case, then the total width of the process will be sum of the individual partial weights gamma alpha plus gamma beta. Now compound nuclear reaction cross section, which is the reaction cross section for the formation of compound nucleus, is the summation of reaction cross section and scattering cross section. Once we know this, then we can get the reaction cross section for the decay channel of the compound nucleus through a particular channel. So if the decay channel, if you want to estimate the decay reaction cross section through the decay of the compound nucleus through beta channel, then the expression for the compound nuclear reaction cross section will be sigma of alpha times to beta. That says actually alpha is a formation channel and beta is a decay channel, will be equal to cross section for compound nuclear formation times gamma beta by gamma. Gamma beta by gamma is actually called as branching ratio, which tells us actually the amount of fraction out of the total width. Reaction cross section in terms of logarithm derivative, we already revised it. That is given by this expression, sigma r equals pi by k square times minus 4kr times imaginary part of rho naught divided by real part of rho naught square plus imaginary part of rho naught minus kr whole square. So the important thing is the numerator contains imaginary part of rho naught, and that imaginary part of rho naught must be negative. If that is not the case, then reaction cross section will be negative, which is meaningless. So reaction cross section is a measurable quantity that must be positive. So in order to make that imaginary reaction cross section positive, imaginary of rho naught must be negative. So that's the information that we can get from the equation 6. And if you look at the expression, that imaginary part of rho naught, if that becomes 0, then entire reaction cross section will be 0. That means there is no reaction. So if there is a reaction, then imaginary rho naught cannot be 0. Then only case when reaction cross section will be maximum when real part of rho naught will be 0. So let us assume that case arises for one particular energy. This is called as ER here, denoted as ER, resonance energy, at which the real part of rho naught becomes 0. If E is the projectile energy, then rho naught can be expressed in terms of a series as rho naught equals P times E minus E naught and minus IQ plus so many other terms. Now look at this expression. Rho naught is a dimensionless quantity. That tells P must have some dimension and Q must be dimensionless. Now the dimension of P, if you do the dimension analysis, P must have the dimension of energy inverse and Q must be a dimensionless quantity. So with all this information, now one can neglect the higher orders of E minus ER because their contribution will be negligible. So neglecting that, rho naught can be written like this. Rho naught equals P times E minus ER minus I of Q. So from that we can get real part of rho naught to be P times E minus ER and imaginary part of rho naught to be minus Q. Now using equation 7 in 6, the reaction cross section simplifies to where we are actually putting back the real value or imaginary value of rho naught here. So the numerator becomes positive and denominator is replaced by P times E minus ER and imaginary part of rho naught is replaced by minus Q. So that if you're simplifying that, you get this expression and divide this entire equation by Q square, correction P square, you get this expression, reaction cross section to be equal to pi by K square times 4kr times Q by P square divided by E minus ER whole square plus Q plus KR whole square by P square. Equation 8 is an important thing. We will be using that. So equation 8 is again rewritten here. To substitute that in some terms of known quantities like partial widths, let gamma alpha be equal to 2 kr by p and gamma total width will be equal to 2 into q plus kr by p. Note that these are assumptions and the product 2kr is a dimensionless quantity and 1 by p as a dimension of energy. Therefore, gamma alpha as a dimension of energy. Similarly, in the case of k, in the case of gamma, numerator here is actually a dimensionless quantity and denominator as a dimension of energy inverse. So again, this total width also has a dimension of energy. And from this relation, gamma beta equals gamma minus gamma alpha, one can get the value of gamma beta. Just algebraic simplification, one will get gamma beta equals 2q by p. So substituting all this value in the above equation, reaction cross section can be simplified and that equation will become sigma r equals pi by k square times gamma alpha times gamma beta divided by E minus ER whole square plus gamma by 2 whole square. This is the reaction cross section, an important equation and represented by equation 9. Remember this equation. Now let us turn to scattering cross section. We have written down this scattering cross section in the initial slide, which is written like this. Now this scattering cross section has two parts, and the first part is actually proportional to non-resonant case. Therefore, that is denoted as amplitude of that is denoted as e power 2ikr minus 1, and the resonant part is proportional to the second part in the above equation, which is equal to 2ikr divided by p minus e minus er plus I by I into q plus kr, where we have substituted the value of rho naught and ik, everything in this expression. So, what is important, near resonance, when E equals ER, the resonant amplitude is much greater than the non-resonant amplitude. Therefore, non-resonant amplitude can be neglected near resonance. So, in such a case, then sigma cross-section for scattering cross-section depends mainly on the resonant part of the cross-section. So, in that case, this expression is become like that. Note in this expression, numerator is an imaginary and denominator also has imaginary value, but it is modulus square. And squaring those and one can remove the imaginary part. So this cross-section, scattering cross-section now will be pure real part. And again substituting the value for gamma alpha, gamma beta and gamma total gamma which we used earlier, we can get the scattering cross-section to be by this expression. Gamma scattering equals pi by k square times gamma alpha square whole divided by E minus ER square plus gamma by 2 whole square. Now ER is related to mass m of the resonant particle through this relation ER equals mc square. So this is actually a resonance case, and the resonance a state will be created that's called as resonant particle whose mass can be equated to and measured by this expression, Einstein's energy equation. The compound nuclear reaction cross-section is just a sum of scattering cross-section and reaction cross-section, and we have derived both. Therefore, compound nuclear cross-section can be written in this manner. Okay, substituting and taking out the common factor, and we know that gamma alpha plus gamma beta is total with gamma. Therefore, compound nuclear reaction cross-section can be written in simple expression like this, which is equal to pi by k square times gamma alpha divided by E minus ER whole square plus gamma by 2 whole square. This equation 13 is the first Breit Wigner formula. Now reaction cross-section is actually the decay of the compound nucleus through particular channel beta. If that is the case, then the reaction cross-section is just a ratio of gamma beta by gamma times compound nuclear reaction cross-section. So using that, one gets Breit Wigner second formula, which is equal to pi by k square times gamma beta times gamma alpha whole divided by E minus ER whole square plus gamma by 2 whole square. So equation 13 and equation 14 are the two Breit Wigner formula. Therefore, those two are actually important one to describe the resonance feature that is observed in the nuclear reactions. Very important reaction possible. So energy distribution of unstable nucleus decay through beta channel near resonance is actually represent this above equation represent simply energy distribution. That energy distribution is given by the Breit Wigner relation. That relation, if you analyze properly, that relation is actually a Lorentzian curve as shown in this plot here, which is similar to resonances which is observed in all other natural processes like resonances in electrical circuit, in LCR circuit, or resonances in other phenomena. We get all this kind of familiar structure. So if you observe this particular case properly, the cross section is maximum sigma m at a particular energy, which is resonance energy. So one can get gamma sigma m by 2. From there, actually one can measure the width at full width at of maximum. That defines the gamma. So gamma basically is the full width at of maximum, which is the characteristic of a particular resonance that is taking place in a nuclear reaction, exclusively represented by Breit Wigner curve. So this is what it is predicted by Breit Wigner formulae, and that is the things which is observed in the case of many nuclear reactions. Here is an experimental result of neutron capture cross-section for indium-115 displaying a strong resonance at an energy of 1.46 electron volt. So this is extracted from the Goldsmith et al. Work. So one can easily observe this particular resonance here taking place. So that's a characteristic of a resonance process in a nuclear reaction. So far we have considered only the resonant part of this scattering cross-section. The scattering cross-section also has non-resonant part, and that non-resonant part is actually has a very deep in just before the resonance. So that is actually observable even from experimental also. So in one of the experiments, this is the experimental data showing a dip as well as rise in the peak. So resonance can be, if the non-resonant part is not negligible, this kind of effect can be observed in the case of nuclear reaction. So the prime uses of Breit Wigner formulae is in optimizing the production yields of some isotopes and in analytical techniques of certain process and in the creations of nuclei beyond A equals 4 in stars. So in all such cases, Breit Wigner formulae can be used. Not only here, Breit Wigner relations are also useful in the case of elementary particles where many types of nuclear resonances will take place. Generalized Breit Wigner formulae. So while deriving Breit Wigner formulae, we made several assumptions. Now if we don't make such assumption, how actually Breit Wigner formulae takes place, modifies. So in one of the assumption is to use only low energy projectiles. Instead of low energy, if higher energy projectiles are used, then higher angular momentum contribution will also be included in the nuclear reaction. So if that is the case, then the reaction cross-section modifies containing this part angular momentum contribution to the nuclear reaction. In addition, we also ignored the spins of the projectile in the target. If we include the spins of projectile in the target also, then the above expression 15 is be generalized to this expression, which is equal to gs of j times pi by k square whole times gamma beta gamma alpha divided by e minus er times L whole square plus gamma by 2 whole square. In this expression, J represents the total angular momentum of the resonant particle. A resonant particle arises when the compound nucleus is formed through the reactants. So this J is the total angular momentum of that particle. And that Gs of J is a statistical spin factor that includes the effects of angular momentum and spins of the two interacting particles. So that is given by 2j plus 1 divided by 2sa plus 1 times 2s capital A plus 1. Sa is the spin of the projectile, S of capital A is the spin of the target. Okay. So there are actually quantum numbers of the two nuclei. When Sa and Sa both spins are 0, then Gj is simply equal to 2l plus 1. So all our assumptions which we have made earlier, they are valid under these conditions. Under low energy and when the incident particle and the target spins are 0, then the Breit Wigner formula which was derived is still valid. So that ends the lecture. Thank you for